Anyway, I can start introducing myself, not because it's a long story, but just to wait for the computer. So I'm Jean. I'm a full-time employee at CSCS doing scientific visualization. I think there are few people like that at CSCS. Actually, I think I'm the only one doing full-time visualization at CSCS. Over the years, I've gone through different visualization software. Most of it, in any case, was always driven by the need to have open source offerings, such that for you, the users of the computing center, there would never be a problem of license and such. So there are many softwares I could name, but in most recent years, Paraview, actually ever since I arrived here, I've always used Paraview, so it's almost 20 years that I use Paraview, since version 0 point something. I still have the CD-ROM actually of that earlier version. Then for quite some years, Visit was also used quite a bit. The interest in Visit has decreased in the most recent years. However, some of the stuff we're going to see today, Conduit and Ascent, they come from the same group that has developed Visit, the group at Lawrence Livermore. So if you know Visit, you will probably say, oh, wow, that rings a bell. This used to work really nice in Visit, etc. And you'll see this in the presentation. Now, Paraview Catalyst is the other word that we are going to use often. Catalyst is Paraview Catalyst is an implementation of the Catalyst interface. There could be other implementation, although at the moment there's only one, and it's called Paraview Catalyst. You can use Paraview without Catalyst, and I've done that for many, many years, and I'm still alive, so it means it's a good thing. And Catalyst is just one layer on top of Paraview, which will allow us to do the coupling with our different simulation codes. The previous version of Catalyst, which was until version 5.8, was a pretty, I wouldn't say cumbersome, but was difficult to use because it required a pretty deep understanding of the underlying VTK data structures. So to do code coupling, you would have to know the underlying C++ library, which is VTK, on top of which Paraview is built. So that was a big roadblock, I guess. If you are a simulation, I mean, each of you is an expert in perhaps fluid dynamics, perhaps astrophysics, perhaps another discipline. And unless visualization was a strong hobby of yours, you didn't have that knowledge required to understand the VTK data structures. So that was the barrier to use Paraview Catalyst up to version 5.8 of Paraview. Now, today we're going to talk about Conduit, which is a trivial, super easy to use API to describe data in memory. And the great thing about Conduit is that both Ascent and Catalyst use that same layer of API for the data description. And this is why I thought this was very nice to present both of them in the same afternoon session. All right, so now let's see if I can log in and start the presentation. The presentation slides are available, and you will see all the details here in my presentation. Yeah, so thanks all of you for being here, and thanks also to different teams. Those teams are the people I've mentioned already, the visit developers from Lawrence Livermore, people from Berkeley Lab, Los Alamos, Sandia, and of course Kitware, who is behind the development of Paraview and Paraview Catalyst, and one person at Kitware who is Francois Mazen, who will join me to teach the same tutorial at ISC in Hamburg in a couple of weeks. Here's the agenda of the afternoon. So we are already behind the agenda, but we're going to speed up over here. So agenda before the coffee break, that's what BC stands for. Introduction to in-situ visualizations, examples of the Conduit interface, applying Conduit and Ascent to make images, transform data, extract data, query data, do all the basic infrastructure of Ascent, and then we'll see examples of this. Of course, the Ascent comes with a tutorial where you can already apply those different requirements on some simple toy data sets. And then we have prepared here, I have prepared 3 applications. One of them is a Python-only simulation in 2D, which is trivial to use, trivial to run on our JupyterLab notebook. And you can take that home and play further with it. SPH Exa is one project that is being run here at CSCS with some partners outside of CSCS as well, for example, University of Basel. So this is a project where I have done an interface for Ascent and for Conduit and for Catalyst as an example. And then Lulesh is another source code, open source. It's a proxy app developed by the national labs in the US, which is used also as a demonstrator. So we have a Lulesh interfaced to Ascent and as well as interfaced to Catalyst. After the coffee break, we're going to jump into Catalyst 2. So of course we will have already learned all the required details about Conduit. Catalyst version 2 is based strictly on Conduit, so I will not have to talk about VTK objects underneath. We'll talk about the API, the Paraview Catalyst blueprint, and then the most important piece of it is how to write Python scripts to drive the in-situ visualization. As opposed to Ascent, where the scripting will be done using either JSON or YAML, in Catalyst, we will drive the simulation with a Python script. And to write those Python scripts, we will see that we can use the graphical user interface of the Paraview client running on a simple, presumably a simpler version of your data set, where you can prototype your visualization and then ask the Paraview client to save the Python script for you. And once that Python script is done, and I will show you how to do this today, you'll have to change basically one line of code to tell Catalyst, hey, the data you are using is not read from the disk, but the data comes directly from the running simulation. This will be the one line you'll have to remember, if nothing else, for the whole afternoon. But I hope you learn a little bit more. Again, we'll go through examples with SPH Exa and with Lulesh. I'll show you a video, just to make it simpler. A video I have pre-recorded about connecting Catalyst live to a running simulation. And then we'll talk about cinema. It's not only Paraview Cinema, because cinema is also something that you can do with Ascent. There's one notebook that produces what we call a cinema database of images. And basically, the principle is that when you run visualization in situ, you will most likely make images. But you know, very often when you have a static image, you say, I wish I could see behind the object here. So when you're running in situ, you have a fixed, in most cases, you will have a fixed camera. But what you would really like is to have maybe a camera going around your object so that you can get a better perception of the different objects. That is actually one example of a cinema database where once the data is in memory, once the data is on the GPU, which is what costs the most, you know that moving a scene around, moving the camera around is something that costs absolutely just microseconds, right? So to take advantage of this, we produce actually a database of multiple images which we can then play back once the simulation has terminated. So cinema is available, of course, as an interface option for the output of Paraview, but also in Ascent. And then to close the loop, we'll have the fact that Ascent can also execute a Paraview Python script, such that if you don't like one interface, you prefer the other one, well, you can play around, So this will be the last example we see. So technical details, we've seen that pretty quickly already. You have all received an account, class 1.5 or 1.6 something with a password. The way to get a terminal window on the supercomputer is to SSH to our gateway, li.cscs.ch, and then from there you can directly jump to SSH date. Jupyter.cscs.ch is also an interface we're going to use to get access to the resources. As I mentioned earlier, I have logged in to using each of your username to preset the environment with most of the requirements. And one of those requirements is to create a virtual Python environment. And this is all done, and you find this under your home, .local/shared/Jupyter/kernels. The reservation name we have for today is In-situ. Your account will expire at the end of the day, so anything new that you do yourself, you should copy to a safe place. Everything else will remain because that's in my repository here, which has been cloned into your account. So at the end of the day, you have the slides, you have the PDF copy of my slides, you have access to this repo, which is public, and then you simply clone it for your exercise. All right, so what's in situ visualization? Why do we need it? I guess if you're here in this room, you're already motivated. You know why you need it, right? Most of it is the problem of having to save data that has grown in size so much that it's not worth it to save data as frequently as we would, and it's impossible to save data at a temporal frequency that would respect what the simulation is actually doing. Just this morning, actually, I got a a link to a book that has been recently published. I encourage you to click on that link and download the book. Most of us, I suppose, if you have university credentials, I mean, for example, myself, via my ETH Zurich account, I could get a free download because this is on Springer Verlag, I believe, the editor. Okay, I encourage you to look at this book here. What we're going to do also today is replay some of the Supercomputing 2021 tutorial that was based on Ascent, because there was no need to reinvent the wheel. The tutorial is done very well by my colleague Cyrus Harrison and his co-workers. So we're going to do some of this, and then we'll go through the practical examples. PITSDAINT is the compute resource we have at disposal today. For those of you not familiar with it, PITSDAINT is a Cray XC40 with over, I mean, I've taken this from the internet page, but I think we actually have over 6,000 nodes today. Those hybrid nodes are equipped with the Tesla P100 GPU. Coming online next year, I guess, 2023, will be the Alps system infrastructure, which will replace PITSDAINT. The Alps is also, I guess I shouldn't say Cray, I should say an HPE compute server. So this will be the shape of Alps replacing DAINT next year. All right. In the past, we've all done visualization in the so-called post-hoc method. We would dump data at regular intervals, and then we would, with all the leisure we would reload that data. Most often on a system, we used to have visualization clusters. Well, that at CSCS, that disappeared, I guess 10 years ago, or perhaps even more, when PITSDAINT itself was the visualization server. So at least here, the advantage is that we did not have to move data from a scratch file system of the supercomputer to the visualization cluster. That was the big advantage. But the advantage, of course, of post-hoc visualization is that there was no time constraint. We could reload that data so many times. In particular, those are the visualization here under that link, the visualization tools or applications available today at CSCS. Now, of course, without I/O, no visualization is possible in that particular format. And what I've come to realize is that the true cost of doing I/O is actually accumulation of the solver's I/O and then the visualization. And I'm sure you run your simulations many times until you get the right parameters set up and until the output satisfies your requirements. Well, the same thing for visualization. I've done, nowadays I do a few, 2 or 3 really nice videos per year because it takes so much time. If some of you are practice visualization, not as a hobby but as a job, like I do, you know that it takes a lot of time. It takes tens or hundreds of iterations. Well, that's the cost of I/O. Every time I have to rerun a visualization script, of course I have to pay the price for the I/O. All right, so post-hoc, moving data to the visualization machine. The requirements is, of course, having a very high data transfer. and then having a machine that is almost as capable as the supercomputer itself. In the case of pitch date, we had at least that part resolved. The alternative, you have all practiced this alternative, doing subsampling both in time and space. In situ, the principle of in situ, and here I'm going to start using many different terms. I'm going to say co-processing, concurrent processing, in situ, etc. We'll come to this. So here I've used the term co-processing. The idea is that we can render data while it's on memory. We can extract data and save only the products of visualizations, which most of the time cost actually many less megabytes or gigabytes of data when saved to disk. Let me make a concrete example. If I have a 3D volumetric box simulation grid, if I'm only interested about a slice through the middle, that slice will cost me n square bytes instead of n cube bytes of data. Okay. All right. Now, if you've already used some in situ visualization infrastructure, you've already come across some of those questions. We're sharing the same physical resource for computation. Does that mean we share the same domain decomposition? Perhaps not. In most cases, now we see multi-processing, multi-threading, multi-everything. So the domain composition might be in millions of subtasks or sub-regions, and oftentimes the visualization algorithms have not been thought, tested, fine-tuned for millions of tasks or sub-objects, and that's going to be one problem. The other problem is what percentage of time can we allow between the simulation and the visualization. There will be a compromise, so there will be the need to do some performance measurement between the time spent by the simulation advancing the simulation and the time spent to do the visualization. Of course, there will also be the problem that some visualization algorithms, which are easy to deploy when data sits on the disk, if I have a temporal suite of data set, it's easy for me to do a particle tracing through time. It just takes a lot of time because I have to load one time step at a time. How do we do this in situ once the data from the previous time step has been overwritten by the current time step? So we'll have to think about all those issues. And of course, if we're going to save less data to the disk, perhaps that data needs to be, how should I say, we should put some glue around it. We should add some information about that data so we understand how it was generated. A third paradigm is actually possible, available. We've talked about post-hoc visualization. We've talked about in situ, where I have implied that I would share the same computer resource between the solver and the visualization. The third alternative is actually to do in-transit visualization, where instead of here saving data to disk at regular intervals, or doing some visualization, feature extraction at regular interval, and saving the result of the visualization to disk, The third alternative is in transit, where I will momentarily stop the solver for the solver to transfer its data to an alternate compute resource. That compute resource will do its visualization. There might be some idle time, and that's fine, but at least the solver, as soon as the transfer of data is done, the solver will be able to continue. So in transit will be the third option. And preparing this tutorial, I thought, next year I should do just in transit visualization. So I hope you'll come back next year. There. Now, does in situ mean in place? Again, I've implied that I was using the same resource. If the data is moved to a different set to a concurrent compute resource, is that still called in situ? We're stretching the definition of in situ here. So those are the different terms I've already used today, and if you look at the literature, you see all of those terms used. So a couple of years ago, Hank Childs from the University of Oregon has grouped together about 50 of us to write a paper, a taxonomy of visualization, of in situ visualization systems. And that's this paper which you can download at this address. And in this paper, we said in situ processing is everything where we process the data as it is generated. So that includes in transit, that includes the strict in situ mix of simulation visualizations running on the same compute resource. In this paper, we've tried to describe the systems along different axes of a definition. The first one was integration type. Second one was proximity, defining how close the data is from the algorithms actually being implemented. Axis was another axis of definition. Division of executions, I've mentioned that already, the time sharing or else. Operations controls, this is where we have to think about what do we actually want from our visualization extractions, and do we want to enable a human interaction with the simulation. And then there's also the output type, which can be of different forms. So for integration type, of course, we had the precursor of in situ visualization system, which were the bespoke implementations where things were very much hardwired into a simulation code, and that has been done since already the 80s of last century. Then we have dedicated API or multi-purpose API, and then we have in terms of integration the so-called interposition or inspection ways of accessing to the data. All the details are in the paper. It's actually a quick read, but it's pretty nice because it really gives you the whole gamut of implementation which you can find. In terms of proximity, of course, you have on the node. You have on the node with a GPU. You can have distinct compute resources. You have, again, multiple flavors for that axis. In terms of accessing the data in memory, as you can expect, there is, of course, direct access and the distinction between shallow copy and deep copy. I hope it's clear to everyone, the difference, yeah? Or else you have, of course, indirect access. In terms of executions, we've mentioned this: space subdivision, time subdivision. in terms of operations controls, is it automatic? Is it fully automatic, fully batched control? Or is there the possibility to interrupt? Is there the possibility to steer the simulation? This would be another possibility. And then, of course, the distinction between blocking or non-blocking access to the simulation. And finally, the output. Okay, output is this one. We have different types of output. We have the so-called subsets. I've given an example earlier. We have an output which is of a fixed size. For example, if we're saving images, those images always have the same resolution, so they cost the same in terms of bytes per second for the transfer to disk. Or you can have output which is proportional. If I do an isosurface computation and I want to save that to disk, there might be time step where that isosurface is null. There's 0 to save to disk. So there we have to also play with that. And since we're talking about saving data to disk, what is a feature? A feature is hopefully most of the time something much smaller than your data. I've taken here an old picture from the days I was doing a lot more aerodynamics. Around this big airplane, the only feature of interest was actually this vortex core here on the wingtip. Okay, so detection of that particular feature is where we're going to be most interested in the in-situ interface. How do we define that particular condition? And in Ascent terminology, we're going to call this a query. That's not surprising. And then it's one thing to do a query, but it's another thing to actually trigger an operation once the query is positive or negative. So they're called exactly this in Ascent vocabulary. Triggering the execution of a particular algorithm will be something that we need to pay close attention to because it's potentially very expensive. All right? So it's not going to be a toys exercise and a child exercise to do this in situ instrumentation. All right, out of the paper, in the paper, 15 of the existing systems which we reviewed, about more than half of them, I believe, use the so-called time division with on-node proximity. So it's really sharing a unique compute resource and then having a very close access to the data. This was the implementation method used by half of the systems. Examples of those are Ascent, Paraview Catalyst, Visit LibSim. LibSim is a system which we published in 2011, so that's, you see, time has gone by. We have already 11 years of maturity for this LibSim interface, LibSim library, which was closely integrated into Visit. Paraview, or the precursor of Paraview Catalyst, is actually from 2000. I reviewed that this morning, 2010. So quite a bit of experience there. There's one system that is very interesting, Sensei. I actually taught a Sensei tutorial here at CSCS a few years ago with a collaborator from California. Sensei is actually a system where we describe the interface to the data once, and then we're able to use multiple back ends for the visualization, and that's quite a nice interface as well. And then there is Adios. Adios, we all think about Adios as a library just like HDF5 to write data to disk, but Adios can actually do a lot more than just writing data. We can integrate Adios into our solution, and we have together, sorry about that, we have together data storage, data staging, data compression, data reduction. We have multiple algorithms embedded into the Adios library, and then we have different transport systems such as FlexPath, data space to do in transit and to do some fancy interface with the data while the data is in memory, and that's the important part. All right. To get more details about Sensei, I recommend the Supercomputing 2021 tutorial notes, where you'll have a mix of Ascent and Sensei presentation. Now, each of you has a particular simulation software in hands, in development. What about my model of internal structure for the data? Is the visualization API, can I map my data easily or transparently to the underlying data? Possibly, and in that case I would use the so-called data adapter. In the case of alternate data representations, I would use data converters. And the problem today is that now we're doing, for example, in meteorology, ensemble computation, so collections of data. We use machine learning on our simulation while we do simulation. We have multi-physics code. We have really a pretty heterogeneous set of data, and those are going to pose problems because there's no direct interface to the data representations in the solver and in the visualization API. So we're not going to talk about this today. We're going to concentrate on the so-called mesh of gridded points. Now, it's still pretty generic. Some of you here in the room have a code that is based on SPH, so there's not even a mesh, just particles. Fine, we can deal with that. Everyone else here in the room, if you have a mesh of data, be it curvilinear, rectilinear, AMR, multi-grid, multi-block, all those different flavors, we can deal with it with Conduit and Ascent and Paraview. So we're going to jump right into Conduit. Conduit, as the name says, is a channel to pass data from one place to the other. Now, we're not going to pass, hopefully, the heavy data. We're going to pass a representation of the data, and that's going to be the key focus of Conduit. Conduit is open source, developed by Lawrence Livermore, and actually the last words I've had with Cyrus Harrison, who is one of the lead developers, is Cyrus told me, we're not focusing only on visualization. We use Conduit for a lot of our multi-physics code to do data exchange, memory to memory, data exchange between codes. So Conduit has that strong emphasis. And doing in-situ visualization is just one example, one scenario of doing multi-physics code coupling. All right, so this is where Conduit comes very strongly. Nice thing about Conduit, it supports, this was the requirement from Lawrence Livermore. It needs to support all 4 languages in use at the lab. So C, C++, Python, and Fortran. Good. Conduit is a convention of usage to transport data, to represent data. Now, just like HDF5 or NetCDF, all of you have used one of them, one of HDF5 or NetCDF, right? Okay. So how do you store your data in HDF5? You and I can store our data in the same data in multiple different ways. And if I give you my HDF5 data, you cannot read it because you don't know what convention I've used. Where did I put my coordinates? What are they called? Is the coordinates array called coordinates, or is it called cores, or is it called XYZ, etc.? Those are conventions of usage. In climatology, there is the CF conventions. That's exactly it. It's a way to describe in a very strict manner that data should be stored in one particular way, such that if I produce my data with software A, I can read it and consume it with software B, because I'm based on that convention. Same thing with Conduit. We're going to have the mesh blueprint, and the mesh blueprint is going to say, if I respect this blueprint, I can produce a description on machine A and consume it on machine B with software XYZ, and it will all work. And it's very nice because the mesh blueprint also has methods to help you verify that your data conforms to the convention. So we're going to do this, and in the code, we're going to actually call that verify method to make sure we pass it in the right way. Now, of course, I can click on the different links here. I should go directly to the illustration of the mesh blueprint, and you'll see how it looks. Or rather, no, I think that's fine. That's fine. I should simply perhaps make this a bit bigger for you to see on the screen. All right, so at the top of my page, the mesh blueprint, a set of hierarchical conventions to describe mesh-based simulation data. So we have many examples, and really there are great examples. So your first exercise when you're finished today, going back to your own code is going to say, okay, I have my own data, it needs to fit the mesh blueprint convention. You look at those examples, and then hopefully you'll have an example that matches the data descriptions which you have in your own code. So there it is. I was giving the example of HDF5. What do I call my coordinates array? Well, the mesh blueprint tells you it should be an object called coords set. And then there's one object called topologies. And then the scalar and vector field and tensor field associated with the data, they are stored under a tree called fields, etc. And then the state will be, I think you got the picture. It's a convention of usage to follow as you store data in the in the conduit convention.
Jean, a question. What are material sets?
What are material sets? There can be, well, for example, solid, air, gas, etc. So there are simulation codes where inside a single cell, computation cell, there are actually multi-materials. That's what they are. I will jump now to the conduit example because I think it fits. Let me close this for a moment. Yeah, that's exactly it. We're going to jump on Jupyter Lab and look at the first conduit description. You're welcome to follow along using your class account. Okay, so my GitHub repo has been cloned onto your home already. There are instructions on what I've actually done. Okay, I've created the virtual environment, I've loaded some modules, etc. All of those should be set up for you. We're going to use that particular page, jupyter.cscs.ch, to log in. We're going to go to the Ascent intro notebooks subdirectory, and we're going to execute the notebook called 02 Conduit Basics. So yeah, if you have not done yet the login, I encourage you to do so. And as I've done here, I'm going to jump to the notebooks intro. Those notebooks have been prepared by the Lawrence Livermore folks. So I've basically copied them locally here at CSCS to test them, but you can actually run that. If you have Docker installed on your desktop, on your laptop, you can actually run those directly without an installation, a physical installation. Let's look at the second actually notebook, 02, which is called Conduit Basics. And we'll see directly the interface here with Python, of course, but in C++ or in Fortran, it's going to be the same really intuitive interface to create conduit nodes. They're called nodes. So my very first cell here is this import conduit cell, and then I was going to say strangely, but there's nothing strange about it. They're tied together, NumPy and conduit. All the data I'm going to pass to conduit nodes are actually NumPy arrays. And in C++, if you have an std vector, you're going to pass that std vector to the conduit nodes. So it's going to be pretty much the same. In conduit data model, a node holds a hierarchy of objects, and it's pretty much like a Python dictionary. We give it a key, and we give it a value. And this can be a string, this can be a numerical, this can be a floating point number, this can be an array of numbers, it can be pretty much anything. We are very flexible about that. So I'm going to now execute that cell over here. It's taking an awful long time here. I wonder if it got lost. I'm going to create a node called n, give it a key, and I'm going to print that using the YAML interface. We can mix and match descriptions between using JSON or using YAML as a language interface. Now, as my cell has been executed, I have here my object called indexed by a key, which is called key, and its value is the string value. There, we have created our first conduit node. Is anyone having difficulty in logging to PitchDate and executing those notebooks? Ah, very good. That's actually my second, I have a slide just for that. Import error, right? Over here on the top right corner of your page, the default kernel is the Python 3 kernel. You need to change this. Oops, sorry. You need to change this by double-clicking here, select a new kernel, and you change your kernel to your new kernel, which should be available from your private environment, and this is called my-env-kernel. I've used exactly the same names as we have in the documentation at CSCS. You're welcome to call it with a different name if you want to. Okay, so that's the key to resolving this error. You need to restart your kernel. Is that better? I'm using a class account here, so if it works for you, it should work for you. If it works for me, it should work for you. Does it work for anyone? Aha, okay, very good. It just worked. Okay. Sorry. Let me continue. I mean, the demonstrations are here on the screen, and then I'll go through some of your desktop to see if there is something obscure that I have overlooked. Okay, my first conduit node has been created. Now, the neat thing about conduit is that I can build a hierarchy all in one shot. For example, over here, I'm going to create a node with a hierarchy called directory 1, directory 2, value 1. This will be my new key, and I give it a numerical value as value. And there we have now a tree, a description of dir1, dir2, val1 with that particular value. So this is now, you can imagine now that describing my data, my simulation data in memory is going to be exactly this. It's going to be a tree. I'm going to have my coordinates. I'm going to have my x, y, z arrays. I'm going to have my field. I will have a hierarchy with my density, my temperature, my pressure, my whatever. All of this arranged in a hierarchy. Now it gets more fun when I execute the next cell over here. I'm going to create a NumPy array filled with zeros here as an initialization. I'm going to fill up that array with the Fibonacci series. And I'm going to say, take the address of this NumPy array, A, and use that with the key Fibonacci to construct my conduit node. And when I print this node, I have under the key fib, I have the NumPy array 0, 1, 1, 2, etc. Okay, so there, this is the first step. I can now store a simulation array into the conduit node. But you're going to ask, wait a second, is it a full copy? Is it a pointer only? And the answer is, in this case, it's a full copy. But Conduit actually supports a, what do I call it? Shallow copy of arrays. So we're going to do the same experiment here, again with array A1, a NumPy array, filled up with the same Fibonacci suite. We're going to create a second array A2, exactly the same initialization, so the arrays contain the same data, but we're going to use two different keywords here. We're going to set the first one, and it's going to be a deep copy. So I use the string fib deep copy to declare my intention. And with the second array, A2, I'm going to use a set external. And this will be a shallow copy. When I attempt to change the last element of the array, indexed by -1, we're going to see the result. There we go. The result is exactly this. The deep copied array has not been modified, and the shallow copied array has been modified. So there we have, in this is the end of the notebook. We now know how to describe our data and how to share memory pointers between our simulation memory organization and a conduit node. The next step will be to pass this node to Ascent or Catalyst. All right? So I'll go to the notebook number 1, which is the first green light notebook. We're going to render a sample data set with Ascent. Make sure the kernel that you use is always my environment kernel. We import Conduit. We import the blueprint to verify that we did not forget any special convention. And we're going to import Ascent. I'll do this right away. The blueprint package also has a set of examples. So one of them is the bread example. This is all documented here at this particular address. Basically, with the bread example, we can specify the type of elements we wish to create. So in this case here, we're going to create a mesh, a three-dimensional mesh, 50 by 50 by 50 in ijk directions. It's a mesh it's a mesh based on hexahedral elements. And we're going to return a mesh, a conduit node. So we execute this. And I could very well here show you the mesh like this. Okay, that mesh has a state. Remember, this was part of the convention. It has a time value. It has an iteration number. It has a coordinate set. The coordinates are explicit because this is an unstructured grid. We have an x, y, z array for the coordinates. We have the topology here of type unstructured. All those are specific keywords of the mesh blueprint. The elements of shape hexahedra, we have, of course, a connectivity list, as in all finite element code. And then for the fields, subnode, we have one scalar array called bread. Its association is vertex, which means that the data is located at the vertex of the grid instead of at the center of the cell. And it has an array of values, etc. We have another field called velocity with the three components of velocity. There. We're going to pass this mesh node to Ascent. So we open Ascent over here with some optional parameters. And then we publish the mesh, which means we actually we pass the data to Ascent. And this is where we have to define now what to do with the data. So we defined the so-called actions. The first action is to declare a scene. And in that scene, we're going to put a pseudo-color plot of variable over here, the scalar field that we had defined earlier, of the field called bread. So this is our action. We add a scene, we add a plot to it. This is the type of the plot. And then you're going to say, how did I know those different names? All of those are documented in the Ascent page. You'll see there are examples for each and all of those different plot types, etc. So it's pretty simple to go through. And then finally, we want to make images. So we're going to define an image name over here, First Light Render 3D. We can print that. This is for our own curiosity here this afternoon. And then we execute Ascent with the particular action node. Let's do this. Over here, I've executed my cell, and I print my action tree. And as you can see here, this is nicely formatted YAML tree add scene, one scene called S1, one plot called P1 of type pseudo-color. Okay, so now we have here a container for plots. We can add multiple plots, and we can add multiple scenes, and we will add triggers, and we will add queries. All of this, we will build our visualization program, so to speak. Ascent comes with a method called the Ascent Viewer to show a particular image. So let's look at this, and this is what you should have on your screen. This is the front-facing view of this cube of data with the variable bread that is being colored between blue and red. So this is the first representation that things are, the first confirmation that things are working as advertised. And then we close Ascent, and we're done. So we have defined, using one of the pre-baked example, we have defined a 3D mesh with different fields. We have defined a visualization script, which included a scene, a plot, and an action to save the visualization to an image. We have published the mesh to Ascent, and then we have told Ascent execute. Now, if we had time-dependent data, the same would happen. Our data in memory would be updated, of course. At each iteration step, we would publish our mesh and then tell Ascent to execute, and then Ascent would execute with the new data. Any questions right off the bat here? John?
This is mostly for... it looks to me like Conduit is doing what XDMF used to do, but in a much nicer, cleaner, modern way. Would that be a reading?
Yeah, it's a good metaphor. XDMF, for those who don't know it, is an interface which actually does what HDF5 doesn't do for you. I gave the example earlier. You can store data in multiple ways in HDF5, and if you don't know where you put a particular array in your HDF5 hierarchy, you don't know where to find it. XDMF is a wrapper. It's usually or always, it's always human readable. XDMF is human readable, and it tells you the mesh is of a certain topology, the mesh has a certain number of scale fields, and they are stored in that particular place in the HDF5 dataset. So that's a very good point. Yeah, Conduit is very much like XDMF.
Just to follow up to that, Conduit is a totally separate library from Ascent, yeah? Conduit is just a description of the data, and Ascent is an interface into the rendering backend. Okay.
So if you're doing code coupling, you can use Conduit without Ascent just to pass your data between your two simulation codes. Okay? That's very good. That's very good. Yeah. So here's our first example. How am I doing with time? Okay, we're doing good. We're doing good. Another question? Yes?
Does Conduit only work with CPU array like NumPy, or it also works with keep by array?
So in this example, which is based on Python because we are in the Python world, we naturally use NumPy because it's the most efficient way to store data. But you can feed to Conduit data that is stored in a different way. Okay. I gave you the example of C++ earlier. If you have an std vector, for example, you give it that address, the address of your vector. Okay. We're going to see that through some of the examples I have prepared. I'll go to the Conduit, the notebook number 3, which is examples. That's pretty good. Let's do it. Always make sure you have the right kernel selected. I'll execute this. First example is creating a uniform grid with a single scale field, so a 3D mesh, single vertex, associated field named alternating. Okay, so the mesh blueprint tells us that I expect a Conduit node with the following keys, coord sets, and then you remember that with Conduit you can declare a hierarchy of nodes all in one shot, so you don't have to do intermediate allocations or declaration here. In one shot we use that key. The mesh is of type uniform, and then we give it the dimensions for I, j, and k. Of course, for a uniform grid, all you need to have is the origin and then the dx, the spacing between grid points. This is exactly the definition here. We have an origin x, y, z, and a dx, dy, dz for the spacing between vertices. We add a topology. Well, of course, in this case, it's implicit, but we still have to say it. The type is uniform. And then we make up an array. This is an example. So we make up an array fields. This is the name of the scalar field, the second key. Association, we've seen what it is already, vertex, topology, and there we go. We use the shallow copy set external with the array vals. Arrays was defined earlier here, so that we have our mesh is fully defined here. Now, just in case it happened to me yesterday, I called mass, M-A-S-S. I used one of the key, I put 3 S's. And when I ran the simulation, I guess it was Catalyst told me, wait a second, your mesh is not conformed. And I'm like, come on, I've done this for months now using the same simulation. I just added the mass array yesterday. It's because of a typo. I had keys that did not match. So typos happened, errors happened. There's our descriptions to the uniform mesh, type uniform, dimensions, origin, spacing, etc. And here's our array. And just because errors can happen, we have the conduit blueprint mesh verify. And if this passes, that's great. If it doesn't, in this particular node, it actually tells you where the error is in your description. So you can then solve it by looking at the error message. We verified our mesh. Now we create our Ascent object. Now we're becoming familiar with it. We publish it. We add a scene, a plot, a pseudo-color plot. The variable is called alternating. By default, we will save data in images in PNG format. We execute it, and then we show the image. It's this alternating 1 and 0 every other vertex, so that's the image you get here. And as a bonus, in the Ascent viewer, you actually have the action. You actually have the action that corresponds to the images you've seen. So those are the actions we have published.
Curiosity, Jean, the warning, is that significant? The one in pink
No,
up above? No.
I've had that for a month now, and
Okay,
I
that's
don't
just a
have time to-
feature.
don't
Okay.
have time to fix it. It was just to verify that the audience was watching. Yeah, I'll get rid of it someday. Next version maybe. There, we close and we're done. We could go through the exercise. We'll do quickly the unstructured mesh made of tetrahedra. So we construct 3 different NumPy arrays for the XYZ coordinate. Here the coordinates type is explicit. We shallow copy the arrays to the XYZ field of the conduit node. It's pretty much the same. Interesting here, the first variable, var1, has an association of element. So it's the scalar field is at the center of the tetrahedra. Same thing for variable 2. We create this, we print it over here, we verify it, we push it to Ascent, and we visualize it, and we have 2, is it 2 or 4? I forgot. Looks like 4, doesn't matter. Tetrahedra here, rendered in our image. The example here is interesting because it creates The next example, 3, it creates a time-dependent representation. So we have a simple definition here where we modify only the contents of the NumPy array that is passed to a conduit. The rest of the definition doesn't change. So this is just a loop over time. Here we take a mesh conduit node, initialized just like we did earlier, as a mesh of hexahedra, and we store that into the conduit node called mesh. And I want to show you the loop. There we go. For all time steps, we update the NumPy array with this particular function. We update the iteration number of the conduit node. So this is under state and cycles. The image file name will be indexed by the iteration number. And we publish and execute. So inside the loop here, we publish and execute. Okay? Now, we have a time-dependent simulation. We're going to generate a series of images. In this case, at every time step, we're going to make an image. It's pretty cheap because it's a toy example. So we have 19 images, or 20, since I see here the last index. We're going to load our images in the Ascent image sequence viewer. Perhaps I've zoomed a bit too much on my screen, but there it is. It's animating through my different images. Okay, nothing fancy because it's really a toy example. And by the way, those images are stored on the disk, so they are right here on the left side of your browser. You would actually see all of those images. Okay. Things are pretty clear? Yes? Good. I'll go back to my presentation here. Here is a Docker, the syntax for accessing the Supercomputing 2000, no, actually the examples from Ascent. All those examples, number 1 through 9, I guess they are. If you have Docker installed, you can run that actually directly from your laptop without the CSCS compute resource. So this is something you could also do tomorrow as you want to repeat this. Under the tutorial link, you see the password for that site. The password is learn. It's written there on the page, just in case you forget, on the tutorial link, if you want to run that Docker example. We've done the first one, the first notebook. You've seen the time generating, we've seen the generating time step, multiple time step example. Rendering images, we've seen it's probably a repeat of some of the things we've already seen. We're going to jump to transforming data. This is pipeline number 5. And then, yeah, and then we'll go back to over here. So number 5, I said, transforming data. We're going to do, now each of those notebooks, by the way, in the very first cell, you have the pointer to the documentation of Ascent. So for scenes, you have the pointers to scene. For pipelines, you have, for queries, you have a page dedicated in the tutorial hosted at Lawrence Livermore. So it's very, very simple to use and follow those examples. So as earlier, with my environment kernel, I'm going to execute the first cell. I will create the same example, always my mesh of unstructured cells of type hexahedra. And then I'm going to do what one of the first example in visualizations that you would want to do, and that is there we go. We want to do an ISO contour of the scalar field. So that ISO contour is called a pipeline. We transform the data with a pipeline. So it has a type, it has a special key called contour in our case. Because it's an ISO contour, it expects a set of thresholds. So those thresholds are ISO, the so-called ISO vals here, defined as an array with two variables. We could have as many ISO contour values as we wish. In this example, we only have two. The field to be ISO contoured is the variable called bread. And for each of the different algorithms transforming data, we will have the similar syntax. We will have a pipeline index, a pipeline name, and then a set of parameters. And they will always be called params. Okay? So that remains pretty, once you've learned one, you've learned most of them. And then we want to do a pseudo color of this ISO surface. The only difference between the previous case where we did a pseudo color of the overall grid, where we use this syntax, a plot, a variable, and a file name. The only difference is that we add a key under the key called pipeline, and we give it the pipeline 1 defined above here in my definitions of pipeline. So this modifies the pseudo-color plot. I've already printed here the actions, the corresponding actions. The pipeline is here, the of type contour with the following ISO values, and then we modify the pseudo-color with the pipeline PL1 defined above. So what we see here is a YAML description of the tree. It took me a couple of weeks, I guess, to understand the benefit of using the YAML interface instead of the JSON interface. You can do one or the other. The first one, JSON, is more error prone. Let's put it this way. So I recommend, and it's written in the documentation of Conduit, we recommend using YAML. And at first I thought, why? You play with it, and then you'll see that very quickly that YAML is the easiest path to completion. Let's look at the second example, combining multiple transformation. If you're used to, let's say, Paraview, we've mentioned it before. We write a Paraview pipeline, we write a visualization pipeline by reading the data, applying one filter, applying a second filter, and so forth. This is exactly what we're going to do here. We're going to combine first a threshold and then a clip. So we had a pipeline. The first pipeline is indexed by the key PL1, and that's the threshold. And sure enough, I told you it would have a key called params. And to threshold, we give it a minimum and a maximum. So this is our example here. Minimum value, maximum value. The second pipeline, which takes as input the result of the first pipeline. The second pipeline is indexed by the key F2. It clips with the following parameters, and it's going to clip a sphere with a particular radius and center given above. And we're done with this definition. We declare multiple scenes, if I remember well. The first scene, S1, is the pseudo-color of only the result of the first pipeline, PL1. So we're going to see the threshold image. Okay, we will execute. Actually, let's do it so that you can follow me. Here's our data set, thresholded. Okay, doesn't make much sense. It's a toy example. In the following cells, example 3, we're going to create again the same pipeline 1, pipeline 2, and we're going to apply at the bottom of my definition here one scene, S1, with the result of the first pipeline, a second scene, no, I mean a second plot, I'm sorry, with the result of the pipeline 2. And we'll see the difference in the visualization. There we go. So we have, oh wait, I got a little bit confused. No, we have here the thresholded data, and we have in blue and red here the two ISO contour. Perhaps I read wrongly. Let's look at the actions. Oh yeah, I'm sorry, the action was actually an ISO contour. So we see in blue the isosurface of 0.2 and in red the isosurface of 0.4. What matters is that in the same scene I have multiple plots. So this is what this example wanted to demonstrate. And then I close it when I'm done. I've lost my page here. I guess that's the convention, not a convention, but in most interface done with Ascent, we will declare a standard visualization, a prototype of visualization that will be used, that will be run by Ascent by default. If you want to do something different, if you want to modify the default scene, at runtime we can supply different scenes. So you will see Ascent will look for one or two files called Ascent action dot JSON or YAML, and it will read that to override the default behavior. I recommend YAML lint to control your syntax. And then I recommend in my repo, in the example Lulish, I have made here an example of an Ascent action YAML, which itself calls a whole visualization program based on the trigger which is defined over here. So this is how we can run a simulation with multiple visualization scripts. Which one is which? It's mostly the same thing, but one of them is JSON. This is YAML. You see, it's a bit simpler. We've gotten rid of all those braces which are impossible to keep track of, and this is what I recommend to use. So the scene description, S1 plots, one pseudo color of the field density, one render action with a file name based on the iteration index. Here I've used two different examples just to show you the possibility. You can define your camera by telling where the camera looks at and where the camera is positioned, or you can use the more intuitive azimuth, elevation, roll, pitch, those things which move the camera along the hemisphere around your scene. Those are different ways of specifying your camera position. So here's a more complete example here. This is one pipeline called PL1 with one particular filter indexed by F1, a filter of type threshold, which takes a minimum value and a maximum value. The scene description specifies the particular pipeline, so it will do a pseudo-color mapping of the field density based on the result of the pipeline F1. So let's see now how I've done this very concrete matter with this SPH EXA project, which is co-developed here at CSCS. We've learned that the first thing to do is to describe our data via a conduit mesh definition. So those links point directly to the source code on GitHub. This is what's in the code. We have, so the code here is C++. So we've looked at Python examples. Now we go to C++, but the syntax is identical. We declare a mesh to be a conduit node. We give it an iteration step number and an iteration value. Okay, those are two different. This is the value of the time step. This is the number of the time step. Because this project is about an SPH solver, we have an explicit set of coordinates of points in space, particles in space. So we define the coordinate sets x, y, and z values to be a shallow copy of the pointers in memory, which I get passed to me via this variable called d. A little bit of a complication here is that the array actually the array is actually a concatenation between different partitions. So we have a start index and an end index. So to tell Conduit that the data of interest starts at one particular index, I pass a shallow copy of the pointer, and I give it the address to the pointer, and then I give it the number of elements, so n minus start for this particular example. The data is stored at the vertices, because we only have vertices in this case, we have particles. And for each scalar field of interest from the simulation, we have an association. Here's the name of the field, density in this case. The values are again a shallow copy to the array in memory with exactly the same syntax as earlier. And we have here a long list for every variable in the code, every variable that you wish to publish. This doesn't cost anything, it's just a pointer. So you might as well publish all the different variables you have, and then if you use them in one scene description, then Ascent actually knows where to find the data. That was my first point, the mesh definition. The second one is the scene definition. So same thing, I'm pointing directly into the source code of SPH exa, and I define here my scene as a conduit node. Everything is a conduit node. That's the nice thing about it. Jean-Guillaume.
Can you go back? That's the volume dependent.
Go back where exactly? This one, conduit mesh. Yes. Yes, good point. Volume depend this question. Actually, I kind of feared somebody would ask. I haven't really understood what it is. It's documented. Every example I've used, they use false, so I just used false. Okay, I'm sorry, this is a bad answer, but seems to be the default. I have to dig further into the documentation to understand the true meaning of that. This is what we're talking about, volume dependent. Yes, yes, it's something like this, but I myself had to understand what this principle would be.
For instance, the field is density, and now you could have a scene where you plot mass. So you could use density to plot mass because you could multiply times.
You derive one from the other. Well, yes and no. Actually, Ascent has its own derived fields subsystem. So you can define variables such as mass derived from density and so forth. So this is why I wasn't sure exactly of the difference between a derived field and a volume dependent variable. I'll dig further. You have motivated me to dig further into the questions. Okay, so we were looking at the Ascent, the scene description. Those are particles which I want to color by density. And well, I don't know why it's called threshold, because I don't see any threshold here. We're just plotting the variables. Fine. We set the camera, the lookout point, the position point, and the up vector for the description of this particular scene. This is actually part of the scene which I wrote a long time, a couple of months ago, and I don't use that anymore. I override that with some other scripts. But this is an example of a standard scene description you could do for your particular data. At the end of this scene description, I have a description here for an extract action. And this is exactly what it is. We're going to, in Ascent, there are multiple ways to actually publish the data. One of them, through the relay interface, is the option to write data in HDF5. So there's HDF5 again in the discussion, and that's very nice because it's a very powerful API to write data. So by adding this particular action as an extract, we simply say we want to export the particles to this particular file name, and we use the blueprint mesh HDF5 format. This is a particular convention of HDF5 using the blueprint that was defined with the visit software. At the beginning of the discussion this afternoon, I told you that some or most of the people who have developed Visit are actually involved now in developing Ascent. So the blueprint HDF5 format is actually completely supported by the Visit software, the Visit visualization software. So I can read this, and I have actually one of the notebook example where I write the data as blueprint and I read it back with Visit. There, that's the, one more line, this is commented out at the moment. Instead of saving the data, instead of saving all the particles, if I want to save a subset of particles, all I have to say is I want to save the result of that particular pipeline, the PL1 pipeline, which contained my threshold operator. So this relay interface gives you the option to save any type of data. It can be the original data, or it can be the result of a query, threshold, etc. It can be the result of a series of multiple visualization filters. Yeah, in total, that's about 150 lines of code. And it's not difficult code. Based on this conduit interface, the ability to define this hierarchy of actions and scene in a very simple manner, we put together basically an interface which enables visualization with very few lines of code, a couple of pages of code in this example. And the example from the previous slide about saving data to HDF5 gives you the idea that we can save data in parallel without writing any I/O code, which is actually a pretty good point, because for many years I've helped with people writing, debugging I/O code. When people don't want to write I/O code, they want to write their simulation stuff. The I/O is always the bad boy in the equation. Okay, in summary, my particle set is defined like this, as a coordinate set with explicit type, with x, y, z value for the coordinates, and it's shared via shallow copy pointers. The topology is of type unstructured. In this case, we only have particles, so the shape is point, but we've seen earlier examples where we had hexahedra, tetrahedra, and so forth. We have a connectivity list, which, by the way, has a certain cost, because the connectivity list is given to Ascent with the normal set API, which means it's a copy of that array, because the simulation itself does not hold a copy of this connectivity array. This is basically a linear array from 0 to n-1, but Ascent needs it today. I think in the future, I'm hoping that in the future we will be able to describe particle sets without a connectivity array, because in VTK itself, there is an effort now to, how do we say, update or upscale the status of the point set class, which has been private and an object that you could not instantiate in the past. I wonder if it's already in version 9.2, you can now actually declare and explicitly a point set, an object of class point set, and with that you do not need a connectivity list. At the moment, this is what we have to live with. Finally, the physical data, here an example with the density field called rho in this particular example, and shared via the domains rho array. We've seen the example, and the code, the extract node from SPH-exa, we've looked at it just a few minutes ago. In Python, you would do something very similar. Import from Conduit, import the relay package, verify that HDF5 has been enabled, because it's by default, I think it's turned off. At CSCS, I have compiled Ascent with the Cray HDF5 parallel library, so it's enabled. And if so, you can save your data, save your mesh, your Conduit mesh node. You can save it to HDF5, and it looks just like this. If I do an H5ls of my file name here, it's a group with a data set, with a hierarchy, a group for fields for each variable, another hierarchy, etc. So nothing surprising if you know the HDF5 format. Supplementary material. This is great. I've made this example, which you find on the notebooks, called Jacobi Python. So we have here, it's a 2D simulation only. We have a conduit mesh definition. Here I'm pointing directly into the code description, and you will recognize exactly the syntax we've seen before. So this is Python now. A uniform grid. It's 2D, so it only has an I and a j for dimensions. it has a particular origin and spacing. And I've made 3 different versions of the code. Each of them are there as a notebook for you to play with. One of them is serial, so it runs with a single task. Then we add Ascent to it. So you see the difference. I've actually subclassed the original simulation class where I add the Ascent definition. And then the third version is the parallel version. And the difference in the parallel version, for example, would be the origin of the grid, because the domain is divided among multiple NPI tasks. Each of them, it's a 1D subdivision in space. So you will see in the code that the origin of the grid is actually shifted in the y direction. The scene definition is pretty trivial here. We have a 2D set. There's not much you can do, but you can do ISO contour lines on a scalar field. So you could actually do this as an exercise, modify the Ascent action, the Ascent scene definition, to add ISO contour of the temperature field between 0 and 1. Those are the variations of the temperature data. The second example, supplementary example, is the instrumentation of the Lulish code, which implements a set of explosion in a quarter of a domain. Same thing, you have a mesh definition, you have a scene definition, and then you have multiple scripts which you can apply to the example. I will take a few minutes to actually go to those examples because we have time. Okay, Ascent intro. So this is in the clone of my repo under examples. We have the Jacobi Python. We have both straight Python code, and then we have Python notebooks. The very first notebook is this, and I use matplotlib to display the data. And here you will probably get an error when you import matplotlib. Okay, this is done on purpose for you to actually understand how this is all set up. First of all, let me see if it works for me. Otherwise, I will make a bad example. Okay. So matplotlib is missing from your import path. Well, on PITSDate, matplotlib is available as a module. Now, you've defined a private kernel. Yeah, actually here, it works even without it, but I want to show it to you. I want to point you to the PITSDate instruction. This is how I've set up your environment. I have loaded the Date GPU module. I have loaded CrayPython. I have loaded Jupyter Utils to be able to create my private Python environment. I have installed IPyKernel with Cinema Science version 1.5.4 only, and I have created my private kernel over here. And yeah, and then the rest is I've cloned my repo. Okay, so over here, no, actually, it's not over here. It's over here, In this file, home.local, share, Jupyter, kernels, my environment, the launcher is where you place all the modules which you want to use in your private kernel. So if you add module load matplotlib at that particular address on pitch date, you will get matplotlib. A long way around, but so Jacobi Python is this. We were there. I've defined a Python class called simulation, which uses a simple 4-point stencil over the domain. And I have then refined that class definition with Ascent. Basically, it uses the simulation initialization as earlier, and it adds the node definition based on Conduit. Okay. At the very end, you have the option between doing the standard simulation with no Ascent output, or you can switch to the simulation with Ascent. You pass the resolution you want, the number of iterations you want, and if you do this, you will have a matplotlib image saved on disk. To make sure everything works, instead of using my private area of the Scratch file system, you would have to use here a path on the Scratch file system which you can modify. For those of you who do not have an account and you don't know the specifics of CSCS, this would be, for example, for username class 159, this would be the temporary space available on the Scratch file system at CSCS. Okay. In parallel, there's one little trick. Okay, you get MPI 4Pi standard, but you have to import Ascent.mpi. For curiosity, you can check about Ascent.mpi. My class definition here is exactly the same as the serial version. And then the parallel simulation class refines this by changing the resolution of the grid, passing the communicator to the Conduit node. So this is part of the options that you have to build your Conduit node. You open Ascent with those options. I've mentioned that the origin in the y direction would be shifted by the rank of the MPI job, and the rest is the same. So for this, you can run, of course, now we have, it's not quite the same. To simulate one-time step, we do the original simulation step, but then we have to do copy data between the boundaries of the processor, and this is done with this send receive code, which I have here debugged for you. Okay, so those are examples that you can run also outside of PitchDane, because there's nothing specific here. I assume on your own laptop, for example, you'll have matplotlib available as a support library. Okay, I've tried to come si dice, stringere, to speed up a little bit because we started late. We're more or less on time again. So I invite you to the break, and please ask questions during the break so that we try to maintain our schedule. Okay? Good.